So now we complete the connection between the matrix trace and the operator trace. And this is sort of a neat one because it gets under the hood a little bit of the structure of an operator. So for an operator T, and we're assuming finite dimensional because I'm talking about matrices, the trace of T is equal to the trace of the matrix of T. Okay, so for the proof of this, if you recall, in the clip 69-3, we discussed the decomposition of V into the direct sum of the generalized eigenspaces. So there's the G lambda k is the generalized eigenspace for the kth eigenvalue. And each of these generalized eigenspaces is invariant under T. So that means, in fact, that T decomposes as a sum of operators, where each one acts like the, actually, each one has one generalized eigenspace that it acts on, and then everything else is in its null space. And so you can break T apart as a direct sum. You might even see this in some books. So it's written as a, they use the same symbol for breaking apart the operator. We don't need to get into that here, but it kind of helps to understand what's coming up next, which is that the matrix of T decomposes as a block diagonal matrix. So a consequence is that each of these generalized eigenspaces has a basis in which T restricted to just that eigenspace is upper triangular. So if we look at the matrix of T restricted, so it's just an operator from G lambda k to G lambda k, then we're going to have some matrix where it's going to be constant down the diagonal. It's going to have lambda k in each diagonal entry like this. And then it'll have whatever it wants to have up above the diagonal, but below the diagonal, it'll all be equal to 0. And so if dk is the multiplicity of lambda k, then this matrix is dk by dk size. Okay, so if we assemble, putting all these together, what does that mean for the full matrix? We get what's called a block diagonal matrix for T. Where each block is of this form we just specified. So putting all this together, the matrix of T looks like, and let's see, so we're going to have some big ol' honkin' matrix here, and so we'll have like a lambda 1 block, and it'll have who knows what up above the diagonal here, and then we'll have the lambda 2 block. So lambda 2 will be repeated according to its multiplicity, and there'll be some stuff here, and then there'll be, you know, all the other eigenvalues, blah blah blah, until we get to the last of the distinct eigenvalues, lambda m, and stuff here. And so each there's these blocks, square matrices on the diagonal like this, and each one of these little green guys is an upper triangular matrix, and out in the hinterlands there's nothing but 0. And so this is what a block diagonal decomposition of an operator looks like. And so written in terms of this basis, you can see that if you were to take the vector of, sorry, the matrix of some vector, then because we've got this block right here, it's only going to affect the entries in the first D1 slots. If we go on, and here I'm going to make the next one say blue, and the next one say orange, then these entries will be the only ones, the only place where there'll be like non-zero computations happening is when they meet up with the ones from this block. And because it's positioned on the diagonal, the output from these, again, will be exactly in those same slots. And so you have this kind of breakdown. And so you can see that the first matrix entries only, first vector entries only ever meet up with these matrix entries and only ever affect these matrix entries of the output, and so on and so forth. And so that's how T decomposes. Okay, so we don't actually need any of that. I just wanted to paint a little picture of kind of like what's going on. But we do need this block diagonal form for the matrix of T. And so each one of these corresponds to an invariant generalized eigenspace. And there's a basis, right, we said, in which each of those gives you an upper triangular matrix. So when we collect the bases for each of these g lambda k's, and just collect them all together, we get a basis for all of V. And this was actually some exercise. It was 2.B exercise 8. So going way back to the very beginning of the course. And then in this basis, notice that in the completed matrix for MT here, the eigenvalues of T appear on the diagonals of the blocks, but since the blocks are on the diagonal of the entire thing as well. Appear and they appear by multiplicity, because the size of the block is exactly the multiplicity of the eigenvalue. And so then that tells you that the trace of T, which is the sum of the eigenvalues, is equal to the trace of this matrix that we've just written down here, this block diagonal thing. But then by our previous result, 10.15, it's independent of basis. And so This completes the proof if V is a complex vector space. And then if V is a real vector space as usual, then we just do this entire argument applied to the complexification of T, and we get the same result.